See, magnet is very interesting chapter. So you have to, if your basics is clear, definitely you can attempt all the questions. But here the condition is that you have to be sure about your clarity. And whenever you are calculating, you have to take care of two things. One is whenever you are calculating the magnetic field, so you have to take care of the direction. And when you are talking about, so when you are calculating magnitude, so you have to take care of magnitude. When you are calculating direction, so you have to be careful about calculating direction. So basically what is happening here, we start with biosawart law. So what is biosawart law is that we can find out magnetic field dB because of any length of the wire. So this is what mu naught by 4 pi I dl cross r divided by r square. So here dl is vector quantity and this is, we are taking magnitude of r square. We are taking magnitude of r square. So see here you get used to get confused that here put r square or r cube or here r vector, yes or no. So when we are taking here vector dl cross r, this is vector, so this is containing magnitude and direction both, and then you have to write it here r square. So this is the Biot-Savart law. It gives magnetic field at any point from distance r dB. So dB is basically what mu naught by 4 pi I dl. So basically I dl is the current element. In this current is flowing. This is I and dl. Dl gives the direction of this strip. So I dl and cross r and divided by r square. Right now we will play with the direction. How to find out the direction for this current carrying strip? So conductor. So see dl cross r. So you have to do dl and cross r. dl cross r. So what is the direction of dl here? This is in r direction this side. So dl cross r. So magnetic field below the plane. So magnetic field will cross this side. If you understood how to find out direction, so your half of the problem is done. Suppose I want to find out magnetic field at this point r, at this point, so this is p1 point and we want to find out magnetic field at point p2. So what, see dl cross r. So dl is here, this dl is not changed and r is changed now. So r is this side, so you have to take like this, dl cross r, dl cross r. So dl cross r, magnetic field will come outside, so here magnetic field will be dot. Simply, otherwise you can go also by shortcut, that is also working, that just put your thumb in the direction of current and cross your fingers, all remaining fingers. So this is give the cross, so magnetic field. And if this side you want to find out, so dl and you just cross your finger outside, so it will come outside. So magnetic field, this is the thing. Now you have to know how to write all the variations of Biot-Savart law magnetic field equations. So how we can write it? See, this is vector, so write it carefully that you need to mention the vector over here. If you want to find out dB, so you can say that mu naught divided by 4 pi I dl. See, across r is the vector, so we can write is this is, we can write it divided by, so basically we write it here r cube because it is going to cancel out, so change it, r cube. Now so vector r can be written as magnitude of r into r cap, yes or no? Magnitude of r into r cap divided by mod of r cube. So here one magnitude is going to cancel out, so when you are writing in the format of and this is cross, so when you are writing in the terms of unit vector, it automatically it will come r square, which is original format. So what is this? Mu naught by 4 pi I dl, and this is unit vector, so this divided by r square. I am writing directly r square. So this is very important, you should know. So you should know how to correlate the relation. So once you know Biot-Savart law, so there are so many applications of Biot-Savart law about which you have to learn carefully. So we are going to explain the applications of Biot-Savart law. So first one is the current carrying conductor. So infinite current. Suppose there is one current carrying conductor. So this is current carrying conductor. Current I is flowing. So simply first I will ask you what is the magnetic field this side. Just put your thumb this side along the wire and fold all your remaining fingers. So this will be the direction. So this side magnetic field is going to be cross direction, very important. This side magnetic field come outside. So this is magnetic field is dot this side. Now our purpose is to find out direction. So suppose there is a point P1 here. We want to find out the direction. So suppose this P1 point make an angle of alpha with this one end and another end, this makes the angle of beta. So now we can write magnetic field at point P1 is equal to mu naught by 4 pi, and we write this distance is d. So this distance we take is this, d. So mu naught I by 4 pi d, and this is sine alpha plus of sine beta. This relation can give you all the magnetic field. If you know only this relation, so you can find out, you can drive out directly all the relation. No need to remember other words. You can do everything only in your brain within a second. So mu naught by 4 pi, mu naught I by 4 pi d sin alpha plus sin beta. Now I'm going to take another condition, is that, yeah, one more condition is that what people used to get confused over here, that if I give angle with here, so if suppose this angle is theta 1 and this angle is theta 2 and this distance is given d and the current I is flowing in through the wire. Okay, so what I will do, so I want to find out magnetic field at, suppose this point is P3, so magnetic field at point P3 will be mu naught I divided by 4 pi d, and now write cos alpha plus of, sorry, cos theta 1. So this is cos theta 1 plus of cos theta 2. So this relation comes. So this relation is very important. And now we'll play with this relation one by one. Now we have infinite current carrying conductor. So infinite current carrying conductor, this is going to this and this. So it's infinite. We want to find out magnetic field at a distance d. So here, so if the current carrying conductor is infinite, current carrying wire is infinite. So first find out direction. Direction will be cross product. Just fold your hand. So this is the direction of the magnetic field. Now you need to take care of the angle. So if you observe, this is infinite, it will tend to pi by 2. So it will tend to pi by 2. So this angle is going to be pi by 2. This is also going to tend to pi by 2. This angle is going to pi by 2. So in that basic formula, put this relation theta alpha and beta is equals to pi by 2. You will get main relation. So what is the okay? So I want to write like this: mu naught I divided by 4 pi d sin alpha plus of sin beta. So in place of sin alpha and beta, put pi by 2, pi by 2. So this is going to be mu naught I divided by 4 pi d, and this is sin pi by 2 plus of sin pi by 2. So what is sin pi by 2? 1. So 1 plus 1, 2. So I am writing it directly, mu naught I by 4 pi d, and this is 1 plus 1, 2 to cancel out. So final relation is mu naught I by 4, 2 pi d. You have to remember this result directly, because question comes from here directly. So that if the current carrying conductor infinite, so what is magnetic field at a distance d? Because of that, so that is mu naught I by 2 pi d. Mu naught I by 2 pi d. What is another condition is that, suppose our wire is semi-infinite. Semi-infinite means that we want to find out magnetic field at this point distance d. So this point is suppose P1. So we want to find out magnetic field. So this is infinite in one and one side only. So this angle is going to be pi by 2. If you assume another angle, imaginary angle, so this angle is going to be 0 degree. You have to substitute this relation in your basic formula for that: mu naught I by 4 pi d sin alpha plus sin beta. So you will get the magnetic field. So what is the main formula? Mu naught I by 4 pi d sin alpha plus of sin beta. So here I am going to put alpha is pi by 2 and beta is 0. You can put reverse, no issue. So you can just reverse the direction, no issue. So mu naught I by 4 pi d, and this is what sin pi by 2, and this is what sin 0. Sin 0 is 0, sin pi by 2 is 1. So final relation in magnetic field because of semi-infinite wire is mu naught I by 4 pi d. This relation is very, very important. It will help you to find out so many questions. So if you understand how to play with the relations, you can do all the questions directly. So because of semi-infinite wire, magnetic field is mu naught I by 4 pi d. Because of full infinite wire, means infinite wire, magnetic field is mu naught I by 2 pi d. And because of the any strip, mu naught I by 4 pi d sin alpha plus sin beta. This application very, very important. One more application very, very important for J advanced. Suppose what if I want to find out at this point magnetic field. So this is semi-infinite wire, obviously. So I want to find out magnetic field over here. Okay, or even not is semi-infinite. So this angle I had given you. Okay, so we can play with any manner over here. So suppose I had given you this angle. Okay, so suppose this angle is given over here. Okay, this angle is given here. So or we can take another possibility, is that suppose this angle is given over here, that okay, this strips makes an angle with this vertical, this horizontal is alpha. So I'm writing this. Okay, this angle is given alpha, and this angle is given beta. This angle is given beta. So you have to focus on this angle. This angle is beta. We want to find out magnetic field at point P, and this distance is given from the wire, is this distance is given from the D. So how to find out magnetic field at point P? So here you have to just use your science, that what I will do, I will find out plus magnetic field because of this, and we will also find out magnetic field because of this, but because of this component we will subtract the magnetic field. So the negative component of magnetic field come in the picture. So what is magnetic field? So this is not finite length. This is what finite wire. So magnetic field is going to be mu naught I by 4 pi d sine alpha. This angle is alpha, sine alpha, and this is minus of sine beta. Minus of sine beta. So once you will do this relation, you will get magnetic field because of the given strip of the wire. This is very very famous and important relation. If you know, you can solve these questions directly. So you will take care of these relations as well. So now we understood how to find out the direction of the magnetic field because of current in the conductor. Current in the conductor may be saying infinite, or okay, particular length. Now what I am saying, okay, what I am saying, Ampere circuit law. So what is Ampere circuit law? Close integration of B dot dl is mu naught of I. Okay, so what is here I? You need to take care of the I enclosed. So I enclosed. So this is closed integration of B dot dl is okay mu naught of times of I enclosed. B is vector here, dl is vector here. So from using this relation we can find out magnetic field, okay, because of the current carrying conductor as well. So suppose we are taking, there is a wire, the radius of the wire is r, and in this radius of the r current I is flowing. So we take this is capital R, the current I is flowing in this wire. So we want to find out magnetic field at a distance r outside from the magnetic point, okay, from the center of the wire. This is center of the wire. So we want to find out magnetic field at this point. What do you need to do? You need to take this closed loop. You need to take the closed loop around this wire, okay, and passing through this point, okay, which will enclose this wire. So now apply this law. So what is if you apply this law, so what is this? Close integration of B and dot dl. So d dot dl I'm writing over here, and mu naught I enclosed. So if I will ask you what is the enclosed current inside this loop, so this is totally I, because I whole wire is coming inside this loop. So you need to take the whole current, that is I. Now see, B is magnetic field, take it outside, and dl. So if you see magnetic field and dl, okay, so this is okay, theta is not coming here in the picture. Theta will not come in the picture. See why? Because if I will ask you, this is magnetic field. So because of this wire, magnetic field will be what? Magnetic field will be what? Cross this side, magnetic field will be cross. Okay, yes or no? So magnetic field B, and this is close integration of dl magnetic field because of this. See, if you are thinking how this angle is going to be 0, because we have to eliminate cos theta, so cos theta should be 0 degree, and we will take the value of 1. So if you say dl is what here, this is the loop, length of loop at any time. So this is not in this plane, this is okay like this ring in this plane, perpendicular to the plane. So this is perpendicular, this is a ring, a magnetic field will be here. So the angle between dl and magnetic field will be theta equals to 0 degree over here. So that's why I took a cos 0 1, and I had eliminated from here this relation, this term. So B dot dl is equals to mu naught of I. So here magnetic field, what is close integration of dl? So 2 pi r, this is circumference of this loop, so that is 2 pi r equals to mu naught and I. So from here we can find out magnetic field is what? Mu naught I divided by 2 pi. This is very very famous relation, you have to remember this relation. If you remember this relation, definitely you can sort out many issues. So here we have to study about 3 cases. One is one point the outside the wire, one point is on the surface of the wire, and one point is inside the graph, inside the wire. Inside the wire, they are at some distance from the center of the wire. And after that, you have to know how to draw the graph. So drawing of the graph is very very important, because most of the time you just okay, question will give you the graph, and you question will ask you to which of the following is correct for the current carrying conductor, cylindrical wire. So this is also known as cylindrical wire. So this is the application of Ampere circuit law. Some of the time question will ask you directly that what is Ampere circuit law. So close integration of B dot dl equals to mu naught I. And afterwards when you learn about electromagnetic induction, EMI, so there you have to study about the application of Ampere circuit law. So there you have to study about the application of. So now we are going to find out magnetic field because of the current carrying conductor. This current conductor is cylindrical wire of radius r on the surface, on this point. So this point is r here. So again apply the Ampere circuit law. So what is Ampere circuit law? Close integration of B dot dl is mu naught of times of I. So we need to find out magnetic field and take it outside, and dl, and this is again cos 0 is going to eliminate over here. So what is when you take the loop here, this is Ampere closed loop. If you take Ampere closed loop, all current is coming inside this loop. So take it I. What is basically we are integrating dl, we are adding dl the strip of the whole loop. So if you will add all the strip length of the whole loop, so it will come 2 pi r. Just write over here 2 pi r. So mu naught 2 pi r equals to mu naught of I. So from here you can find out magnetic field is what? Mu naught I divided by 2 pi r. Again, this is very very important and useful. If your question comes from your directly, you can solve this question directly. So this is the thing. Another is more important than all these two results. Because why? Because people don't remember that. Somewhat it's difficult to remember it. So that result is mu naught by This result inside the wire result will come like mu naught I by 2 pi r square into r. This result is very important here. Magnetic field directly proportional to r. When you move from center to the towards the surface, so it will be directly proportional to r. So I want to find out at this point, this is the center and this is the capital R. We want to find out at point P magnetic field. So this and whole current is flowing through this wire is I. So this point, so this radius is R. So what is ampere circular law? Closed integration of B dot dl is equals to mu naught of I enclosed. This you should have fluent, okay, fluency. Okay, you have to develop fluency to write all this relation, and you can be a rank over there. Yeah. So B close integration B dot dl mu naught of I enclosed. So we have to find out. I'm taking this outside. B is outside. Close integration of dl. So integration of dl is circumference of this loop. And mu naught, now you have to play with the I enclosed, because here I enclosed is going to change. Okay, so you have to apply just some basic mathematics, then you can find out the basic, okay, how we can find out the current. Okay, so basically what is I enclosed here? See, if I will ask you total area is pi r square, total current is I, no issue in it, because pi r square is the area of this cross section of the wire, and I current is flowing through the wire, and I divided by pi r square. We want to find out what amount of current is going through it, what amount of charge is flowing through it. So even we can find out the charge by differentiating dq by dt is that value. So right now our interest is to find out the charge. Right now I want to find out the current through it. Okay, so what is the area for this? Pi r square. So solve it. I divided by pi r square into a pi r square. Pi r square, pi cancel out. So this is what I r square divided by r square. Now I'm going to substitute this relation over here directly. This is I, and this is what r square divided by capital R square. Now solve this. See, B, and what is integration of dl? That is 2 pi r. 2 pi r. So I'm writing it clearly. So this is 2 pi r equal to mu naught I r square by r square. Now I'm going to eliminate it. I'm solving over here. So see, what relations we can cancel out this r to r from here. So this only one r remaining over here, and this is going to 2 pi r square. So I'm writing here directly now. So this is what mu naught divided by 2 pi r square into r. This relation is very important. So I have shown you the how to find out. Okay, you should know derivation as well. Okay, so you should not ignore the derivation, because if you want to be ranker, you have to know derivation and application both. So yeah, application is important. Definitely you can do that question only, but the along with that derivation is too much important. So you have to take care of the derivation as well. Yeah, now I'm going to apply this for drawing the graph. So how to draw the graph? So for that you have to know all the three relations, then only you can draw the graph directly. So basically what was first inside relation mu naught I by 2 pi r square into r. What was second relation on the surface? Mu naught I by 2 pi r. What was third relation outside? Mu naught I by 2 pi small r. So see, 1 by r is what? Hyperbolic curve. 1 by r is hyperbolic curve, and capital R is directly proportional to r is linear curve. So I'm going to draw it on the curve. So this is r. This is magnetic. What? Okay, let's take it. What this? Okay, yes, this is take magnetic field. This is r. So what I'm saying, inside the conductor, inside the conductor. Okay, magnetic field at any point is what? Magnetic field is directly proportional to r. See here, directly proportional to r. So the graph will be linear, and afterwards its graph will be hyperbolic, because it's inversely proportional to r. So I basically better write a small r, and here what is the magnetic value of magnetic field? This is mu naught I by 2 pi r is the value of magnetic field. This is the graph. You have to be the expert of this graph. Whenever a question comes in front of you, you can solve this question directly. When you know the graph, when you know all the relation, then only you can solve this relation. Otherwise it will be difficult for you to find out the relation. Yeah, this is one thing. What I want to play over here, that if I want to find out magnetic field at the center, so what will be the value of magnetic field at the center? Once we find out magnetic field at the center of the cylindrical wire, so we can apply this relation for any conducting wire, because most of the wire their radius is significant, so we can treat it as a thin wire. So because of thin wire, so this we are playing right now with thick wire. So if the question is mentioning you about the thick wires, you no need to worry about it. You have to apply all this relation without any worriness. But if the question will mention you the thin wire, so in the thin wire radius is tending to 0. So that result I want to find out. Our purpose is to find out, drive out that relation, what will be the magnetic field on the point lies on the thin wire. So for that, what I am doing, this is the strip, this is the cylindrical wire, this is the axis of the wire. I want to find out magnetic field at the center, BC. So for which relation will help us to find out magnetic field at center? This relation? No. This relation? No. Which relation? This relation. So put here r equals to 0, because at center r is going to be 0. So what is magnetic field at the center? Write it. So I'm not focusing over you to remember any result. You have to know, okay, because if you want to rank, if you are aiming for rank, then you have to know the relation, how to find out a relation within a second, microsecond. You can find out all the relations, but for that you have to know. Yeah. So magnetic field at the center is what? Put r equals to 0. So if I put relation mu naught r by 2 pi r square into 0, this is 0. Means magnetic field on a current current at the center is 0. Means if there is a thin wire, any thin wire, if our point is here, so if I will ask you current I is flowing it, so what is magnetic field at point P? Without any thinking, you can write directly magnetic field at point P is 0. But what if any point is outside, but lies on this axis at this one P1? So again you have to write point P1 is 0. Magnetic field at point P1 will be 0. So this is the greatest application of EVA. So you should know. Yeah. So now you understood about Ampere circuit law. Now you understood about the magnetic field biosawart law. Now you understood the magnetic field because of the semi-infinite wire magnetic field, about the infinite wire magnetic field because of finite wire magnetic field because of the some angles. So if the some angles is not missing, some angles is missing from the length of the wire, then how to deal with that question. Now we will play with the circular coil, because most of the time you have to also play with the circular coil. So this is circular coil, current is flowing into it, so you have to know the direction about it. So we'll play at the center. So see, again you have to apply your right hand, put your all the remaining fingers, call your remaining fingers around the circle. This thumb will give the direction of magnetic field. So direction of magnetic field is a cross. If the suppose current is flowing, this is clockwise, you can keep in your brain that if the current is clockwise, so magnetic field at the center will be cross, means below the plane. If the current is anti-clockwise, so if you apply just your apply the thumb rules, and current is going, magnetic field is going coming out. So here magnetic field is above the plane. So magnetic field, if current is flowing through the wire is anti-clockwise direction, magnetic field will be above the plane. Yeah. So our purpose is to find the direction. So this is mu naught I by 2r, mu naught I by 2r. This is very important relation. You should know. You can write this relation using Ampere circuit law as well, but right now no need of that. Just remember this result, mu naught I by 2r. Here we can play with the number of turns. So if more than one turns comes, you have to assume magnetic field because of the each turns produces their own magnetic field. Always keep in your brain, each turns, either that is circular coil or axis of the coil, each turns always produce their own magnetic field. So a magnetic field, because the direction is going to same, okay, at the any certain point, so that magnetic field is going to adding up. So you will add up directly. Basically we multiply the number of turns, what I want to say. So magnetic field because of n turns is mu naught n I by 2r, mu naught n I by 2r. And here you should know what is n, total number of turns. Don't get confused, total number of turns. Yeah. So there are so many possibilities, there are so many questions. We can play with these relations, we can mix with the wire with the straight wire, we can mix the wire with the inner triangular wire. So there are so many possibilities. So out of that, some possibilities over here I am writing over here. But before that, if I will tell you that this strip is any arc, okay, this strip is any arc of first semicircular. In the semicircular, I want to find out magnetic field at point P, current I is flowing through it, so current find out the direction here is cross, radius is r. So what will be this magnetic field? So you can directly say mu naught I divided by 2r divided by 2r into 2, because this is half. You are assuming only the half of the circle, so you have to divide it by 2. So this relation is going to mu naught by I by 4r. You don't need to remember this result, but you have to be aware how to solve. Okay, what about if the quadrant? So this quadrant, I want to find out magnetic field at the quadrant at the point P, and the radius is r. So what I will do, again I will divide by 2, or you can divide directly divided by mu naught I by 2r divided by 4. So this is what mu naught I divided by 8r. Clear? Clear. Tell me clear. So all these relations should be clear or not clear, should be clear to you. And if in all the steps we can play with the number of turns. So if you are playing with the number of turns, you don't need to worry, just mu naught n I divided by 4r. We are playing with the number of turns, mu naught I divided by this is what I am writing, see, divided by 8r. So this is very important for you if you understand this thing. Clear. So if you understand, you relate the relation, it will help you a lot. If some portions not visible, so I can't do anything right now. So first we'll see some types of the questions, how to apply the relation over here, then we'll play with different questions. So what I'm saying right now, suppose R wire is like this, okay, so this, so R wire is like this, okay, so R wire, this is one wire, and this is another infinite wire, and this current is flowing through this. Okay, or if this is like this, no need to worry about it. Okay, this is center. Okay, so current is coming here, and going there. So how to find out magnetic field at point P? So we want to find out magnetic field at point P. So you have to take magnetic field because of the circle, and magnetic field because of the straight wire, because of the wire. Okay, straight wire. So what is magnetic field because of the center? So you need to find out the direction as well, because direction is very important in such situation. So what is direction? Just curl your remaining fingers. This will give you the cross product. So magnetic field point is cross. What about the direction here? Just apply your put your thumb in the direction of wire and just curl your remaining fingers. It will come dot. So because of this this side it will come dot. So what I will do, I will subtract. We will not going to add. Some of the time you have to add, some of the time you have to subtract. You will take care of the values. Okay, so basically because of the center, mu naught I divided by, because same current is flowing through the wire, current may be different. Okay, so mu naught I by 2r, mu naught I by 2r plus of, okay, because of this wire, this is infinite wire, this is infinite wire. So mu naught I by 4 pi dc, here no plus, here is minus. So this is the magnetic field at point P. So if you know the values, if you know the relations, you can find out it easily, no issue in it. Yes, yes, yes. There is one arc. Okay, this is the center. Okay, so now what question will give you like this? Okay, suppose r and is passing through the center. Okay, so this is r one and like this. Okay, so r and is passing through the center like this. Okay, so this is passing through the center. Okay, so here also see, this is the, okay, center of the circle. Okay, and some what we are trying to connect it, so let's connect it, no issue with it. Okay, connect it. Okay, so this is connected like this and like put like this. Yeah, so what is happening over here? Magnetic field, this is the center, this is point P, this is point P. We need to find out magnetic field point P. Current I is coming, going, this current is, this I current is going, this radius is r, and this is infinite. Okay, this is infinite and this is infinite. So this is wire number 1, this is wire number 2, and this is wire number, I am taking this diameter as a wire number 3rd, and this is taking a diameter as wire number 4. So if you see this point P, is lies on this straight wire, lies on the straight wire. So what I said you, if the wire point lies on the wire, so magnetic field, because this wire, current carrying wire, is 0. So magnetic field because of 1 at point P is 0. Magnetic field because of 2 at point P is 0. Magnetic field because of 3rd at point P is 0. Magnetic field because of 4 at point P is 0. Because why? Because this wire is also passing through the center. If you see, it's not exactly passing, but it seems to pass. It seems means you have to assume it. So it will, if you proceed, it will pass through it. So no need to worry about, no need to do a separate calculation. Just you assume that relation, you use separate calculation, that is magnetic field if the point lies on the wire, so magnetic field because of that is 0. You use that relation, no need to worry about it. So this wire is passing from the center, so magnetic field is 0, magnetic field going from the center, magnetic field is 0, coming through the center, magnetic field that is 0, going out from the center, magnetic field because of that is 0. But right now we have to assume only this semicircular ring. So what is magnetic field because of this? So now I am taking what magnetic field because of circular ring. So this is what mu naught by 2r. This